Okay, yeah, thank you, and welcome to my third lecture. So let's start by sharing my screen. Let's see. Okay, so today I want to use conic optimization, which I introduced in the first lecture, to solve some problems in lattice theory, especially the lattice covering problem. For this, I have to discuss a little bit what the parameter space of lattices look like. And this I started already yesterday, and today I want to continue with that. And after we looked at this parameter space of lattices, we are ready to solve or to make some progress on the lattice shear covering problem. Okay, so the parameter space of lattices is nicely described by Voronoj's lattice reduction theory. So yesterday we convinced ourselves already that the space of all lattices is related to the rational closure of the positive definite matrices. And on this rational closure, the group GLNZ acts by conjugation. And this captures that the basis has different kinds of, that the lattice has a different kind of basis, and GLNZ, the orbit of GLNZ goes through all different lattice spaces of a given lattice. And then reduction theory of lattices is nothing else as finding a nice fundamental domain for this group action. Rational closure mod GLNZ. So the parameter space of lattices is exactly this quotient here. And now we want to find a nice fundamental domain for this quotient. We discussed already yesterday a little bit that this fundamental domain will come from some infinite polyhedral face-to-face tiling of the cone of positive semi-definite matrices. And in dimension 2, these will be triangular polyhedral face-to-face tiling, and there all these polyhedra will be G2Z equivalent. And the picture which you should have in mind, at least for dimension 2, is this tiling of the cone of positive semi-definite matrices of size 2 times 2. And here you already see the triangles, and every triangle corresponds to one fundamental domain, and they are all G2Z equivalent. And today I want to show you first how these triangles are defined and how they generalize to for larger n. And this is done by the construction of Vallentin polyhedra. That's the empty sphere construction we already discussed yesterday. So we have a matrix Q, which lies in the rational closure, and then P is a Vallentin polyhedron of Q if it comes by this empty sphere construction. So there is a center C, there's a radius R, so that the vertices of the polytope of the polyhedron just lie on the circumcenter, on the circumsphere here, and all other lattice points lie outside. Okay, and now we put all this Vallentin polyhedron together, which gives us a Vallentin subdivision. It gives us a Vallentin subdivision of the space Rn. So what we do is we take, for a given matrix Q, we take the Vallentin subdivision, which consists out of all Vallentin polyhedra of Q. So all Vallentin polyhedra of Q, which you can construct. This is a polyhedral complex. This lives in R to the n. And for example, in dimension 2, it can look like this tiling of squares, or this tiling of triangles, or this tiling of horizontal strips. Of course, we have to imagine that these tilings go on in all directions. Okay, and then it's a case that different Qs can have the same Vallentin subdivision. And we just assemble now all these Qs having the same density subdivision together, and this is called the secondary cone. So this is a secondary cone, delta of the density subdivision of Q. So these are all matrices Q prime, so that the density subdivision of the matrix Q prime coincides with the density subdivision of Q. In fact, one can show, and that will be part of one of the exercises, that this is a polyhedral cone in the cone of positive semi-definite matrices. And when proving that, we will see that the facets of this polyhedral cone, they are determined by the facets of the density subdivision. So every facet of this polyhedral cone in the cone of positive semi-definite matrices comes from a facet of the density subdivision in Rn. So for example, if you look at the facet here, which is just an edge, of course, in dimension 2, this will correspond to one of the facets of the triangles. And so, for example, also here, this triangular subdivision, you have triangles here, and every facet of the triangle will correspond to a facet of the polyhedral cone in the cone of positive semi-definite matrices. So maybe it's a bit confusing because there are two different subdivisions right now. There's one subdivision on Rn, and there's one subdivision in the cone of positive semi-definite matrices in dimension n plus 1 choose 2. Yeah, but it's like that. Dimension 2, of course, these things are even more confusing because the dimension is the same essentially. But in high dimension, of course, things get different. So we have a subdivision on Rn which induces a polyhedral cone in dimension n plus 1 choose 2. Okay, so some facts about secondary cones. So now we look at the cones, the polyhedral cones in the cone of positive semi-definite matrices. So first of all, this secondary cone is full dimensional if and only if the density subdivision of Q is a triangulation, if it only consists out of simplices. So that's a generic situation when you have a triangulation. Then you have an ordering relation. So the secondary cone of Q lies inside of the closure of a secondary cone of Q prime if and only if the density subdivision of Q prime is a refinement of the density subdivision of Q. So for example, this triangular subdivision here is a refinement of the square subdivision because every polyhedron here lies completely as a subset in a polyhedron over there. And that's basically also the definition of a refinement. Then we have a relation between two different kinds of triangulations where the secondary cones share a facet. So we have two density subdivisions, two density triangulations, del Q and del Q prime. And suppose the dimension of the intersection of the closure of their secondary cones is of maximal dimension if they are different. So it is n plus 1 choose 2 minus 1. That's exactly the case when these two subdivisions, these two triangulations differ by a bistellar flip. So bistellar flip I will also define in the exercise, on the exercise sheet. But I think the picture says more than the definition. So for example, these two density triangulations, they differ by a bistellar flip. Because if you want to go from this triangulation to that triangulation, you simply flip this edge over here, this edge, this yellow edge here, you flip over to this yellow edge over there. And in between, you have a subdivision which is just consisting out of these squares. And so you have to imagine a bistellar flip always like that. that you go from one triangulation to the other, to another triangulation by going through some intermediate phase. And this intermediate phase has Delaunay subdivision where some of the Delaunay polyhedra are not simplices, but there are polytopes having n+2 vertices. And these flips you can do a couple of times, not only once. So for example, you have a situation like this, that you have a flip graph that you can flip, say, from the edge going like this to the edge going like that. But you can flip more. For example, you can flip now the horizontal edge, and you get a flip to that side, or you can flip, say, the vertical edge, and you get this triangulation, and it goes on and on and on. Okay, so now we come to the main theorem of Voronoi second reduction theory. So it says that there are only finitely many n-dimensional Delaunay triangulations up to GL and Z equivalents. So the number of different triangulations is finite. And furthermore, we have the subdivision of the rational closure of the positive definite matrices as the union of all possible Delaunay triangulation of the closures of secondary cones. Yeah, so every secondary cone, every Delaunay triangulation gives you a secondary cone, and then if you go over all possible Delaunay triangulations, you exhaust the entire cone of the rational closure of the positive definite matrices. And if you go back to our picture here, then it looks basically like this, that together with this triangulation here, so together with this triangulation here, the secondary cone is exactly this polyhedral cone. Oops, like this. So the entire polyhedral cone is this big triangle here. And then if you move from this triangulation to that triangulation by a bicellular flip, you end up with a secondary cone, and then you get this extra secondary cone. And on the middle, on the facet between these two things, then you find all positive definite quadratic forms, all positive definite symmetric matrices where the Delaunay subdivision consists only out of squares. And then you can go on and you find the next secondary cone and on, and then you exhaust the complete cone of positive semi-definite 2 times 2 matrices. Okay, and then because we only have finitely many Delaunay triangulations up to GL and Z equivalents, this is enough to have a fundamental domain of this group action. So you might ask why this triangle is again subdivided into 6 triangles. And that's the case because indeed this big triangle is not only is not a fundamental domain, because it has some internal symmetries. And if you factor out these internal symmetries, they are coming by the 6-fold symmetries of this triangulation, then if you factor this out, you find this triangle at the end. Yeah, so this finitely many Delaunay triangulations up to GL and Z equivalents, you have to reduce again by the internal symmetries to get really fundamental domain. But if you're interested about doing optimization of the space of our lattices, then it's enough to have more than a fundamental domain. It's enough to have something bigger, because then you only have optimized over something larger and you don't lose anything. Maybe you do some extra work, but usually this extra work is not too much of work. Good. So then you might ask, I mean, how many different triangulations do we have? And there's a known classification, which is known up to dimension 5. So in dimension 2, there is one triangulation up to DL 2Z equivalence. Also in dimension 3, there's one triangulation up to DL 3 equivalence. But then starting from dimension 4 on, things become more interesting because you have more different kinds of triangulations. So in dimension 4, you have 3 different kinds. And this was all proved already by Voronoi in 1908 in his original paper. Then it took quite some time to find a classification for dimension 5. And it's a result by Baranovsky and Ryzhkov in 1976 that there are 221 plus 1 different triangulations. So it's 222, but it's written 222 plus 1 because in their paper they were just missing one of the triangulations. But later we found out that's only one which was missing. But then in dimension 6, there are many, many, many triangulations. And so far, computer search didn't finish the job. So we don't know how many there are, but there will be many. Millions and maybe even billions. It's not so clear. Okay, so let's look at the application of all this to the lattice sphere covering problem. So here's the lattice sphere covering problem. So how is it given? So given is the dimension. We want to solve, we want to find the best lattice sphere covering dimension n. And then the task is to find the lattice L in Rn so that the covering density, delta of L, theta of L, is minimized. Yeah, and the covering density, what does it mean? Yeah, it means, so you take your lattice, like here on the right-hand side, then you center at every lattice point a sphere, and then you blow up the sphere that it covers the entire space. And then it should be as thin as possible, meaning that if you take a random point in Rn, then the number of spheres which cover this point on expectation should be as small as possible. And for example, in dimension 2 for the hexagonal lattice in this setting, the value is 1.2. So a random point in Rn, in R2, is covered by 1.2 spheres on average. And if you want to see a formula, it's like this. Theta of L, so the covering density of L is given as a fraction mu of L to the power n divided by determinant of L times the volume of the unit ball. So mu of L is a covering radius of the lattice. So that's the distance of a point which is furthest away from a lattice point. Yeah, so that's exactly the radius I have to take so that the sphere centered at the lattice points just cover the space.
Frank, there's a question.
Sure.
Is there an obvious algorithm to find the Delaunay triangulation D such that matrix Q is in delta of D? So is there an obvious algorithm to find a triangulation?
Not quite actually. So there is an algorithm, but it's not obvious. Mm-hmm. And the algorithm will involve some convex hull computation. So you have to compute the convex hull of some points. I think we discussed it also in the exercise sheets.
Okay.
Yeah, I mean, it's not obvious, but it's doable.
Okay.
Yeah, thanks for the question. Okay, so we were discussing the covering density. So we take the covering radius to the power n, and then we divide it by the determinant of the lattice. And the determinant of the lattice is simply the absolute value of the determinant of the basis, the basis matrix. Okay, so that's the parameter which we want to minimize because we want to find a lattice sphere covering having density as small as possible. So what do we have to do? Yeah, first of all, we can ignore the volume of the unit ball because that's a constant, independent of the lattice, only depending on the dimension. So we can ignore this. So then in order to minimize this fraction, we either have to minimize mu of L or we have to maximize the determinant. And in the first lecture, we discussed a little bit the max depth cone. So this will be helpful when dealing with the covering problem. So we are going to maximize the determinant, and at the same time, we try to fix the covering radius. Okay, so the covering radius is the distance of the largest distance of a point in Rn from lattice points, but at the same time, it's also the maximum circumradius of the Delaunay polytopes. Yeah, so that's easy to see because it comes from the empty sphere construction. So that means if you want to say that the covering radius mu of L is, say, equal to 1, because we want to normalize it, and because things are scaling invariant, we can normalize it, then it means simply that we have to make sure that the maximum circumradius of a Delaunay polytope, of all the Delaunay polytopes, is less or equal than 1. And it is achieved at some of the Delaunay polytopes. Which also shows that looking at Delaunay polytopes and looking at the Voronoi second reduction theory makes a lot of sense if you want to study the sphere covering problem. Because the covering radius is immediately related to the Delaunay polytopes. Okay, so some recap of the max net optimization. So max net optimization in kind of an algorithmic framework was first studied by Van den Berg, Boyd and Wu in 1998. So they developed some nice theory. They also developed some algorithms to solve them. So here we are going to work with a conic formulation. So we are working with a cone dn or dn plus 1. And we already discussed how the dual cone looks like. I think on my slides before I had dn plus 1, but it's the same. Yeah, so this, what I had as dn plus 1 is now dn. And the good thing is, as we already discussed, that we can optimize over these two cones, dn plus 1 and dn plus 1, dual in polynomial time and under usual mild conditions, for example, for the Lipschitz method. Okay, so here's the basic idea. So the basic idea is that first of all, we fix the Delaunay triangulation. So we fix the Delaunay triangulation. And then once we fix it, we restrict the lattice covering problem to this Delaunay triangulation. And then it becomes a tractable max net problem. So what are we going to do? So we are maximizing the determinant. Because in the fraction of the covering density, the numerator was a determinant. Then we want to have that the matrix Q we are optimizing over lies in the secondary cone of the Delaunay triangulation. And we take the closure here because we want to have a closed polyhedron. And because the secondary cone is a polyhedral cone, this condition that Q lies in the secondary cone of D is a linear condition. So it can be expressed as linear conditions in Q. Then we have to say something about the circumradius of the Delaunay polyhedra. So now our Delaunay polyhedra are simplices. And now we say that the circumradius of every Delaunay simplex which occurs should be at most 1. So that's a normalization constraint. Things are invariant under scaling, so we can say that all the circumradia should be at most 1. And then this becomes a tractable max net problem. So we are maximizing determinant, we have linear conditions, and we have conditions on the circumradius of Delaunay simplices. And now we have to express these conditions in a nice form, and then we have the possibility to solve the lattice sphere covering problem using optimization software.
Frank, why do we have the condition less or equal 1 and not equal to 1?
So we have different kinds of Delaunay simplices, first of all. And we only care about the maximum circumradius.
Okay. Yeah.
And then, because things are, I mean, if you would have strictly less than 1 for all Delaunay simplices, then you could scale Q a little bit, so that one of the circumradii becomes 1. And then if you scale it, the determinant would become bigger. So, so by saying less or equal than 1, you don't lose anything.
Okay. Thanks.
Okay, but now we have to discuss how to model the condition mu L of Q less or equal than 1 in a nice way. And that's done by this gadget here, which also will be part of the exercises. So the lemma is, suppose we have a simplex where one of the vertices is the origin. And that's enough for us, because if you understand all the simplices where one of the vertices is at the origin, then you understand also all the other simplices, because they're just translates. That is translate of the simplices. Okay, so suppose we have a simplex where one of the vertex is the origin. Then the circumradius of the simplex with respect to Q is at most 1 if and only if the following matrix is a positive semi-definite matrix. And yeah, this matrix looks a bit funny. So it has a 4 on the top left corner. So then the first row and the first column is special. So you have V1 transpose QV1 up to Vn transpose QVn on the row as also on the column. And then here on the center block, you have Vi transpose QVj. And the good thing is, first of all, this matrix should be positive semi-definite. And secondly, if you look at it closely, you see that the conditions are linear in the matrix entries of Q. Yeah, so this is really a positive semi-definite condition in terms of the matrix entries in Q. And this gadget, yeah, I think has a nice proof. It uses Cayley-Memmer determinants. And these determinants are usually used to compute the volume of simplices given the edge length of the simplices. But you can tweak this a little bit in order to make this work, in order to find this gadget which makes sure that the circumradius of a Delaunay simplex is bounded by 1 with respect to a given Q. But this will be part of one of the exercises. So for the moment, just enough to understand that this is a positive semi-definite condition which is linear in the matrix entries of Q. So, or in other words, if you know optimization, it can be expressed as a linear matrix inequality. Okay, and now we have everything together, so that we have some algorithmic approach to lattice covering. So what do we do? Yeah, we enumerate all possible Delaunay triangulations, which are finitely many, up to GL and Z equivalents. And then for every of these triangulations, we solve one of these max-net problems. Then we take the minimum of all, and then we are done. So this we did together with Achel Schirmann some years ago. So we made a C++ implementation of Voronoi second reduction theory. So the program is called SCC for second cone cruiser. It's still working, I heard. Using this, we found all solutions up to dimension 5. And we could reprove and correct some results of Baranowski and Ryzhkov then, using this. For larger dimensions, starting from 6 on, we couldn't finish the computation, simply because at that point there were too many different triangulations. But nevertheless, we found some nice new conjecturally optimal lattices for sphere covering. But yeah, unfortunately, still today, these are only conjectures. And so I think it would be nice to start to work on this again, because now we have much more computational power, much better parallel algorithms and so on. So maybe together with some extra mathematical insights, it would be possible to finish the proof. What is the best sphere covering, lattice sphere covering? So,
Frank, how did you solve the max-det problem?
So I solved it by computer, and I used some very old software which was coming from the code of Wu, Van den Berge, and Boyd.
So it is special for max-det.
It's special for max-det, but now there are better algorithms, and also some STP solvers have the possibility to include max-det.
Oh yeah.
I think something like STPT3, for example, has this possibility. Okay, but you can do much better things now. Okay. So a second thing I want to talk about, and that's the sphere covering problem in dimension 24. So dimension 24, I think everybody knows this in the audience, the Leech lattice. And the Leech lattice, in a recent breakthrough result by organizers, by Marina, and together with Danilo, Avinav, Henry, and Stephen, they proved that the Leech lattice gives the optimal sphere packing in dimension 24, as well as it is universally optimal with respect to energy minimization. For the sphere covering problem, it seems to be the same. So also there, the Leech lattice gives clearly the least dense sphere covering in dimension 24. So clearly, maybe it's not so clear because we don't have a proof, but on the other hand, we don't have any other candidates which even come close to the Leech lattice. But unfortunately, currently we don't have any good methods, like for example the linear programming bounds, to come anywhere close to a proof that the Leech lattice is optimal for sphere covering. But we could at least prove that the Leech lattice is locally optimal for lattice covering. So at least in the neighborhood of lattices of the Leech lattice, there's no lattice which is better than the Leech lattice. And this is now also an application of conic optimization, about an application of the max-det problem. For this we have to understand the Delaunay polytopes of the Leech lattice. And they were classified by work of Conway, Parker, and Sloan, and by another work by Borchardt, Conway, and Queen in the 80s. So we know exactly how these Delaunay polytopes look like. And for us, it's going to be important that there's a class of Delaunay simplices where the covering radius is attained. And this class is called A25. So A25 is the class of Delaunay simplices, the convex hull of vertices V0, V1 up to V24. And the good thing about this Delaunay simplex is that the circumsphere, the center of the circumsphere is the barycenter. And the lattice is basically defined as follows. It's defined by this diagram here, by this extended cosine Winkel diagram. So you have all these vertices which form a simplex, you have them aligned on a circle, so it's a closed circle. Then it's meant like this, that if two vertices are adjacent by an edge in the circle, then the edge length of the simplex edge is equal to square root of 6. So let's explain the 6 here. So for example, the edge length between V0 and V1 is 6, as well as between V1 and V2 is also 6, and so on. So it goes around until the edge between V24 and V0 is equal to 6. And if you don't have an edge, then the length, if you don't have an edge inside of this graph here, then the length of the simplex edge is square root of 4. Yeah, so there are two different kinds of simplex edge length, 6 and 4. And this diagram, this circle gives which are of length square root of 6 and which are of length square root of 4. Okay, and then now we want to give a proof that the Leech lattice is locally optimal for lattice sphere covering using MaxZ. So there was a first proof by Achel Schürmann and myself, which was a bit more complicated. And I want to show you at least a hint how to prove this using the MaxZ framework. And this we did together in a seminar with Stefan Krupp, Jan Rolf, and Max Zimmermann. And yeah, the first and last is also here. So if you want to discuss later the coffee break with them. Okay, so how is it done? So it's done by a MaxZ relaxation. So here is the relaxation we are going to solve. So we are going to maximize the determinant of Q to the power 1 divided by n. Then you want to have that Q lies in the cone of positive semi-definite matrices of size 24 times 24. And we want to have that the circumradius of all simplices of type A25 is bounded by 1. So we take the simplex A25 and then we let the automorphism group of the Leech lattice act on them. So this is all matrices T in the group C0, conway 0. So that's the automorphism group of the Leech lattice. And that's kind of the second condition. So it's a relaxation because, I mean, if you remember the MaxZ formulation which we had before, it was including two other things. It was including that Q lies in some secondary cone. So we just omit this condition here. So there are less conditions, so it's a relaxation. And we also omit the condition that the circumradius of all other simplices, of all other Delaunay simplices is bounded by 1. So we also omit this condition. So two different kinds of conditions we are omitting, so we have a relaxation. And then, because the Leech lattice is a feasible solution to this maximization problem is greater or equal than 1/2. Yeah, so you plug in the corresponding Q for the Leech lattice, and then we'll see that the feasible solution gives you 1/2. Okay, so that's a relaxation. So we're omitting two conditions. So now we want to apply duality theory. So we want to convert this maximization problem into a minimization problem. And because of weak duality, we have that max is less or equal than min. In order to do so, we first of all rewrite this maximization problem into primal standard form, which is done here. So maybe it's too much to read for the moment, but the only thing which happens here is that we rewrite things in primal standard form in order to be able to write down the dual. Okay, so this is done here. So here is again the maximization problem in primal standard form, and here's a corresponding dual, the corresponding minimization problem. So if you go from maximization to minimization, then every equality constraint here for the maximization problem becomes a variable in the dual. And you will see that there are 3 kinds of variables in the dual, corresponding to the 3 kinds of constraints you have here. Now, I think also because of time, I will not go through all the details here, but I will show you the basic ideas of the proof and all the verification you can do later if you like. Okay, but the point now is that we have a minimization problem and we have 3 different classes of optimization variables in the dual, in the minimization problem. And for the constraints, we have 2 different kinds of constraints. So we have one constraint coming from the fact that the circumradius should be bounded by 1. That's the first one here, coming from this gadget. And the second constraint is coming from that we want to maximize the determinant of something. Yeah, there are two kinds of constraints. Okay. Now we want to minimize this. And the good thing is that we can do this completely by hand. So there's no computers needed. We can find the optimal value of this minimization problem by hand. And yeah, we do the following ansatz. The ansatz is given here. So we have three different kinds of optimization variables in the dual. They are indexed by all elements of the Conway group, and the Conway group is rather big. So there are many, many variables. So I think it goes in the millions and even more. But our ansatz is that we simply say that the three kinds we have, we will all set them to be the same. Yeah, so we set alpha to be all variables of the first kind. We say that 2 beta are all variables of the second kind. And we say that delta or 2 delta are all variables of the third kind. So instead of having so many optimization variables coming from all elements of the Conway group, we simply have 3 variables now. Yeah, so we reduced the number of variables very dramatically here. Then we plug things in. Then the first condition coming from this gadget turns out to be the simple condition that this matrix over here in these 3 variables, alpha, beta, and gamma, is positive semi-definite. Okay, so we have a condition of 3 variables and having this big matrix being positive semi-definite, and then by the sure complement will also be the exercise. It's a standard trick in conic optimization, especially semi-definite programming. And using the sure complement, we can simplify this condition to have at the end the condition between alpha, beta, and gamma, which is over here. Yeah, so that this matrix is positive semi-definite boils down to the fact that this inequality is true. This inequality between numbers is true. So this deals with the first condition. Now the second condition is a bit more complicated. So the second condition comes from the fact that we want to maximize determinants. And then just gives you the basic idea. So then we are going to rewrite these terms corresponding to our ansatz. And if we're going to rewrite this term corresponding to our ansatz, we have especially to look at sums like here. So maybe I highlight this. We have to look at these sums here, this sum and this sum. So what is a sum? Yeah, this sum is simply, we take all vectors E and S4, and S4 is the shell of the Leech lattice, where our lattice vectors have square length 4. And we take these vectors E times E transpose. Of course, everybody in the audience knows how many summands we have. The same we do also for shells of length, squared length 6. And now we have to compute these matrices here. Yeah, so we have to compute the sum of this 196,560 vectors, and we have to compute the sum over the 60 million vectors. Okay, this is doable. You can do it by computers, but you don't have to. You want to do things by hand. And here now, the next trick is going to help us. And the next trick is that we're going to use spherical t-designs. So what is a spherical t-design? Yeah, a spherical t-design is, these are vectors on the unit sphere, which are good for approximation or interpolation of integrals. So this point set has the following property. So if you want to integrate a polynomial of degree at most t over the unit sphere, then it's enough to compute the average of f over this point set. And if the point set X has this property, then it's called the spherical T-design. And spherical T-designs are very nice. They're related to nice configurations on the sphere, like the n-gon, the simplex, the cross-polytope, the icosahedron, the root system of E8, or also the shortest vectors of the Leech lattice. And these have different strengths corresponding to the largest T which you can put here. And for example, for us it's important that S4, so all shortest vectors of the Leech lattice, they form a spherical 11 design. And these spherical T designs are useful for optimality conditions because, I mean, if you rewrite what a spherical 2 design is, then this is equivalent to say that the sum over all x in X of X sub X transpose is a multiple of the identity. And these are exactly the summands we had in the previous formulas. That we have to sum over all elements of S4, or we have to sum over all elements of S6. And it turns out that they are all 11 designs. So especially, in particular, there are also 2 designs. So we can, in the previous formulas, we can simplify this large sums as multiple of the identity. Yeah, so now we put everything together. It's going to be the last slide. So it's known that all shells of the Leech lattice are spherical 11 designs. So this you can prove, for example, using modular forms, but we use it here as a black box. So in particular, we know that the sums, which looked at the beginning so complicated, are simply multiple of the identities. And then we put everything together and find out what alpha, beta, and gamma is. And here are the numbers. And if you plug in these numbers into the optimization problem, into the minimization problem, you also get a half. And the half is also coming from the Leech lattice for the maximization problem. So you have a half less or equal than the maximization problem, less or equal than the minimization problem, less or equal than a half, which shows at the end that lambda 24 is the optimal solution of this problem, of this maximization problem and of the minimization problem. So in particular, it shows that lambda 24 is locally optimal for the lattice sphere covering problem. Okay, and that's the end of my lecture. Thank you.